So in this lecture, we are going to talk about gradients and Hessians of quadratic and linear functions. In the previous lecture, we talked about gradient of f of x with respect to x, which is equal to partial derivative of f with respect to x1, with respect to x2, xn. And also we talked about Hessian metrics. Something I want to note here, x is a vector. So we mainly focus on the scenarios where the input is a vector of variables. This is also Hessian of x. And something that we note, these two elements are equal, so this is a symmetric matrix. Let's start with the linear function. So we define for x, which is an n by n vector, let f of x, function f of x is b transpose x. So what is b? B is a vector of coefficients b1 to bn. All right. So this is the known vector of coefficients. So this is a linear function. First, I'm going to expand f of x. This will be sigma I from 1 to n b sub I xi. All right. So this is equal to b1 x1, b2 x2, bn xn. So what will happen here now? If you want to find element I of the gradient, so gradient of f of x with respect to x, element I of this is going to be derivative of f of x with respect to xi. If we do that, it's going to be derivative of b1 x1, b2 x2, bi xi, bn xn with respect to x sub I. So what will happen? Derivative of all of this will be 0 with respect to xi. Only this one remains. So we are going to have derivative of bi xi with respect to xi, which is nothing but bi. So this is element I. So gradient of f of x with respect to x is going to be b1, b2, bn, which is nothing but b. Now we are going to write this in the closed form. So in the closed form, what does that mean? Gradient of f of x with respect to x is gradient of b transpose x, which is our linear function, and this is equal to b. All right, this is the first thing we wanted to discuss. The second thing is gradient of a quadratic form. First, we define the quadratic function. F of x, where x is a vector, is x transpose ax, where A is a symmetric n by n matrix. All right, if we want to expand f, it's going to be f of x going to be sigma I from 1 to n, sigma j from 1 to n, aij, xi, xj. So this is the expanded form of this function. Now what we are going to do, we are going to determine what's the derivative of f of x with respect to x sub k. With derivative of f of x, which is sigma I from 1 to n, j from 1 to n, aij, xi, xj. Now what I'm going to do, I'm going to break this into cases where I is not equal to k, j is not equal to k, cases where I is not equal to k, cases where I not equal to k, j not equal to k, and cases where I is equal to j equal to k. All right, let's see what will happen then. Then we will have derivative with respect to xk, sigma I is not equal to k, j is not equal to k. In those scenarios, we will have aij, xi, xj. So there is nothing about xk. Plus, when I is not equal to k. In this case, we will have ik and j is equal to k. xi, xk plus the scenario where j is not equal to k, but I is equal to k. So we have akj, xk, xj, and finally the scenario where both I and j are equal to k. All right, so now let's see what will happen. Derivative of the first term with respect to xk is 0. Derivative of the second term with respect to xk is sigma I is not equal to k, aik, xi. Derivative of this term is sigma j not equal to k, akj, xj. And finally, derivative of this one with respect to xk is 2 akk xk. All right, now what we are going to do, we are going to write this again. So we have sigma I is not equal to k, aik, xi. Another trick that I'm going to do, I'm going to break this term into akk xk plus akk xk. All right, I will write one of them here, plus sigma, sigma akj xj, where j is not equal to k, plus the second one that we factored. All right. So if we add these two together, if we merge this inside the sigma, then we can simply say sigma I from 1 to n, aik, xi, and the same for the second one. We can say sigma I from 1 to n, akj, xj. But we know that A is a symmetric matrix. So we can say this is 2 sigma I from 1 to n, aki, xi. All right. If we look at this in more detail and given the fact that A is symmetric, then we can conclude that, let's go to the new page. We can conclude that the case entry of gradient of f of x is the inner product of case row of A and vector X. So what does that mean? That means gradient of X transpose AX with respect to X is 2A multiplied by X. So if I want to write this in the closed form, it's going to be gradient of X, f of X. F was a quadratic function, so X transpose AX is equal to 2AX if A is symmetric. Now, we notice that the gradient of f of x for the quadratic form is a linear function. And we already know for linear function from the previous one, this is what we had for linear function, right? So let me write this down here again. Gradient of quadratic function is 2ax for symmetric A. And now I want to find the Hessian matrix, which is equal to gradient of 2ax. I'm going to plug this from here. And gradient of 2ax is nothing but the coefficient, which is 2a. So Hessian matrix for the function, the quadratic function, is equal to 2a. All right. Now that we have these, what I want to do, I want to provide a simple comparison between the case that we only had with the single variable calculus calculus. So in the single variable calculus, f of x for the linear case is ax. And hence, gradient of f of x is derivative with respect to x, which is equal to a. In the matrix calculus, we have f of x, where x is a vector, is equal to b transpose x, and gradient of f of x is b, which is b1 to bn. And I want to do the same comparison for the quadratic form. F of x quadratic is equal to a x to power 2, then gradient of f of x is derivative of ax squared with respect to x, which is 2ax. And now we define our quadratic form, where x again is a vector, as x transpose ax, with A being a symmetric matrix. So gradient of f of x is going to be 2 matrix A multiplied by x. So this way you have a general idea of how matrix calculus and single variable calculus could be related. All right. In this lecture, we talked about two special cases of gradient. Gradient of linear function, So f of x is b transpose x. Gradient of f of x is b, where b is a vector. And then for quadratic function, gradient of x transpose ax with respect to x, where a is symmetric, is 2 multiplied by matrix A multiplied by X. And then we had Hessian matrix. So Hessian matrix for the quadratic form is equal to 2 multiplied by A. And Hessian matrix for the linear form is 0. We also provided the comparison with the single value calculus, single variable calculus, to just give an intuitive idea of how these are connected.